Got it? You can come. You got it? Okay, there you go. I will begin with a word of prayer. So here we go. Dear Father, we thank you for this day. I thank you for the students. Just ask you to bless this class, and thank you for keeping us dry in here. In your name we pray, Lord Jesus. Amen. All right. It's a little rainy out there, I suppose. So today I would like to talk to you guys about work, energy, and power. So what I did last class was I just showed you probably chapter 7, to be honest. Well, I'm not. Maybe it's chapter 6. Let me check for a second here. No. I guess you could say I started with the end of chapter 6 last class in some sense. That's kind of the punchline to what we're doing, is applying conservation of energy to solve problems that we have solved, in more clumsy ways in the past. But technically speaking, I really should talk about the concept of work, right? Because the concept of work has to do with energy. It's part of the same story. And sometimes you'll hear people say something like, energy is what? It's the ability to do... Complete this sentence of middle school science. What's that? Work. Yeah, energy is the ability to do work. So that's how energy ties to motion. And so I guess I should probably give you a definition of what is work. So here's what work is. The work done by a force F along a path C is the work, big W. It's the integral along C of F dot dr. Now, obviously, I'm misbehaving. Am I allowed to tell you this to you guys? I'm not. This is forbidden mathematics, is it not? But this is generally actually what physicists think of work being in the mechanical context. It's given by what's called a path integral. And this formula I wrote down, it allows us to calculate the work done by a force which varies in both magnitude and direction along the path C. So the real concept of work, the kind that we don't have quite the mathematics to do in here, it allows you to calculate the work done by something when it's moving along some kind of crazy, twisty-turny path, and when the force acting on it is varying along the path in some kind of complicated way. But, of course, we tell you guys how to do this in what's called math. Well, it's Calculus 3 that you learn how to do this, all right? So that's 3 more semesters of calculus than you've had here, I think, right? Maybe you saw it in high school, I don't know. So we can't do that, right? But we can do the next best thing. So we have to limit our attention to F equals to F naught. In other words, it's constant. Typically, we work with constant forces. There's a few non-constant forces we work with where I just do the calculus for you. For example, the spring force is not a constant force, and yet we study it because I do the calculus for you. I did the calculus for you by telling you potential energy was 1/2 kx squared last time for the spring. All right? That's a result of calculus. But if we limit our attention to the force being constant, then this formula simplifies. So this C is like some kind of, whatever curve. It goes from point R1 over here to point R2, like that. That's the curve. It could do all kinds of crazy stuff. So we have to limit our attention to a constant force along a line. That's all we have the math to do in here, okay? So we limit our attention to F along a linear path. So we're going to go, say, from point R1. Whoa. I am very happy that we're inside right now. You guys hear that? So we're going to go from a path R1, from a point R1 to a point R2, all right? And we go along a line, all right, like this. So this is the curve that we'll study. And then the question is, what's the work done by a force, a constant force, as an object moves from point R1 to point R2? Okay? So the general definition, which I wrote above with unjustified calculus, simplifies, in this particular case, to something pretty nice. The work done is just equal to F naught dot product with the change in R, the displacement, right? Where delta R is just R2 minus R1. So we take the dot product of the force with the displacement to get the work done by the force. That's the same dot product that 21 out of 47 of you could calculate absolutely correctly on test 1. And there are probably maybe 10 people in here who are just genuinely like, what? It's a dot product, from what I saw in test 1. The other about 35 to 40 of you at least know what it is and made some silly mistake, or you just got it right. So I think most of you actually, all of you, certainly by test 2, will know how to calculate this. All right? I will review it momentarily. Now here's a picture. So the force I'm saying is constant. So what's the force look like if I map it? If I draw it here, the force is like this, yeah? If I draw it here, the force is, I'm trying to draw the same force vector. You know, the force is the same along each point in the path. I'm saying apply the same force as we go across, all right? All right, let me give you an example. So let's say we take a box, all right, and I want to apply a force. I'll actually use a pull. I'll pull this time. Pull on the box, force like that. F naught equals to, let's say, 100 newtons, all right? And let's put that thing at an angle of 60 degrees. My picture's not quite right? That's not 60 degrees. It's more like 30, but I want to look at 60 degrees. And let's move the box from here, which say is, and this would be the point, I don't know, we'll say that's at 0, 0. And we're going to move the box all the way over here to the point 5 meters, comma 0, right? Here's the end result over here. So the question I have is, if that constant force of 100 newtons at 60 degrees above the horizontal is pulling the box from 0, 0 to 5 meters, comma 0, how much work does this force do on the box, all right? So we're looking at a linear path. The force is constant. This is the situation where we can just calculate the work by taking this dot product. So in this case, what's the delta R? So this is my R1. This is my R2. So what's delta R? It's really just R2 again, isn't it? It's 5 meters, comma 0. Now what's the force as a vector? How can you write the force as a vector? How do we do that? Now the force, we've got 100 newtons on right here, right? That's F naught. This is 60 degrees. So here's the x component, and here's the y component, right? What's the formula for the x component? What's the formula for the y component in this context? Yeah, I heard 100 cosine 60, 100 newtons times the cosine of 60 degrees for x, which is 50 newtons. Cosine of 60 is a half. And then 100 newtons times sine of 60 gives me the vertical component of the force, right? So 86.6 newtons, something like that. All right. So what's I can actually write down the force vector. What does the force vector actually look like? F is specifically 50 newtons, comma, 86.6 newtons, yeah? And I guess I called it F sub naught. All right, so I have the displacement, I have the force. We take the dot product of these two things to calculate the work done, right? So what is the work done? How do we calculate dot products? Actually, I think more of you had this right than got the angle. I mean, there are a lot of people who got the dot product right who just messed up calculating the angle, right? So actually, many more of you than 21 out of 47 could do the dot product right. In fact, exactly correctly. I would say probably like 30 of you, if I had to guess. Okay, anyway, statistics aside. All right, 50 times, so we got 250 Newton meters plus 0. I don't even usually write the plus 0, but the y times 86.6 times 0 gives me 0. So there's the dot product. And what's a Newton meter? A Newton meter is the unit of energy, and it's also known as a joule. So we have 250 joules is the work done by this force over this motion. Now, I wouldn't recommend that you do this problem this way if I was to assign it on the test. All right? There is a simpler way to think about this kind of problem. All right? For a one-dimensional problem, another way to think about this formula, the work formula. So let me give you an interpretation here. Interpretation of work formula. So I said that the work is equal to the force dotted with the displacement, right? But if we draw a sort of abstract picture of this and say F naught looks like this, and the displacement looks like this, all right? Then we can also write the work in terms of the angle between the displacement and the force, theta, and simply the magnitude of the force times the magnitude of the displacement. In other words, the distance traveled times so the magnitude of the force, F naught, all right, times the distance traveled, which is the length of the displacement, right? And then times the cosine of the angle between these. That's another way we can look at this. So if I revisit my example 1 revisited, we could say that the work done is equal to F naught times the distance times the cosine. And so a lot of times people will use D for distance here because it doesn't give us a lot of joy to write bar, triangle, R vector, bar again for the distance traveled, yeah? Oh, the distance is it's the length of this vector. So I have to take the square root of the sums of the squares to find distance. And in 3 dimensions, it's this 3 square, well, not sure if I've answered your question.
Like how we did the change in R, we did R2 minus R1.
Yeah.
Still the same as the other part where you put E.
It should always, yeah, D should be the distance from the initial point to the final point. So a way to calculate that is to take R2 minus R1 and then to calculate the length of that vector. Does that make sense? The length of the vector is the square root of the sums of the squares of the vectors. So like the length of the vector 1, 2, 3 would be the square root of 1 squared plus 2 squared plus 3 squared and so forth. So example 1 revisited. We have F naught d cosine theta. What's the angle between the force and the, what's the displacement here? If I draw the displacement up in my previous example, it's just this, right? Right? That's delta r explicitly in that previous example. And so what's the magnitude of the displacement? Displacement's a vector. Yep. Oh. It was you were saying 5. You weren't like raising your hand. You were actually giving me the answer, not asking for the permission to give the answer. I got you. So I sometimes teach children in the in the Wednesday, and so I have. Okay, so 100 newtons. That story's not interesting. I'm not going to finish it. 100 newtons, and D is, what was it? 5 meters, and then cosine of 60 degrees, which is, yeah, 250 newton meters. So I think you guys like the FD cosine theta formula. Why? Why do students like FD cosine theta formula? What does it not involve? Does not involve the dot product, does not involve vectors. Why don't you guys like vectors? Why can't students like vectors? I don't understand it. I've always loved vectors. So much animosity towards vectors from the students. I don't know what to say. And it's not just you guys. 231's the same. It's the same thing in there. Even Calculus 3, half the students, they fight tooth and nail not to learn what vectors are. But I tell you, vector is the right way to think about three-dimensional geometry. There are problems that you just can't properly think about without vectors. Here's such a problem. So if I'm going from the point 1, 2, 3 in meters over here to the point 10, 20, and 0 in meters, all right? Suppose I'm doing that, and suppose that we're looking at the force of gravity, which is minus 9.8 meters per second squared times, I guess I should tell us the mass that we're working on. Let's say, suppose the mass is, I don't know, let's say 10 kilograms. So what's the force of gravity? 0, 0, and let's say minus 980 newtons, yeah? So that would be the weight. Then the question I have is, what's the work done by gravity in this situation? So I can picture the force of gravity. It's just, my picture's not very, this picture is very heuristic. Maybe I should, all right, let's make this picture better. Instead of putting 0 over here, let's make that like 30. And then we can at least in our mind picture z as being the vertical direction, right? So you're going from 3 meters in z up to 30 meters in z. How far have you gone up in the z direction? 27 meters, all right? So what's the work done by gravity here? Work equals F dot the displacement. So here the force was 0, 0, minus 980 newtons. The displacement is 9 9 meters, 18 meters, 27 meters, subtracting the initial and final position, yeah. I calculate the dot product, what happens? The first two components don't even matter, right? And we just get minus 980 times 27 meters, right? And so what's the work done here? I don't know, I got to go get my calculator. Oh no! Do. No, I don't. Let's see here. 980 times 27. 26,460. So 26,460 Newton meters. And that minus is important. Why is there a minus there? So work could be negative or work could be positive, right? What is the significance? You know, I started talking about interpretation. I didn't finish the story here. Another way to think about this interpretation is what we're looking at is the parallel component to the force times the displacement. So this is the part. It's the magnitude. Well, it's not that either. It's the component of F naught, which is in the direction of the displacement. That's what work is. It's the magnitude of, the component of the force times the distance traveled. Right? But that's an oriented distance, right? Like if I go from point 1 to point 2, that's different than if I go from point 2 to point 1. If the force remained the same, the work done by that force would be negative, going from one to the other or from the other to the one. Like which direction you're going matters. If the force points in the same direction as the displacement, the work done is positive. If the force points opposite the direction of the displacement, the work done is negative. Right? If the force points perpendicular to the displacement, what work is done? What happens when theta is 90 degrees? Cosine of 90 degrees is? I heard some silent zeros. 0, yes. So perpendicular forces do not do work. All right? So, you know, anyway, so when we look at this one, we've got a negative work. Why did we get that? Because the displacement, you know, the part of the displacement which is matching the force, right? It's in the opposite direction, right? The force is downward, the displacement is upward, right? And that's the only part of the force which is doing work. There's only gravitational force. There's no x and y in this example. Any questions about any of this? There's another way we could do my third example, I guess example 3. We could use potential energy, yeah? Because the work done is also equal to minus the change in potential energy for conservative force. This I'm just sharing with you now. This is a new storyline that we're starting to develop. All right? So work is minus the change in potential energy when the work is done by a conservative force. What's the potential energy here? It's m G, Z, because Z is the H in this problem. So we've got what? Minus, what was my M? 10 kilograms times 9.8 meters per second squared. And so what's my, so the change in potential energy, by the way, we can also write as mg times the change in z. So what's the change in z? Z is what? The initials, the initial, excuse me, the, so I said that the motion was going this way, right? So the final is 10, so it's 10, I mean, words, 10 minus 1. Oh, but I'm looking for the change in z, right? So it's 30 minus 3. That's the change in z. So the change in z here is 27. And of course, that's exactly the calculation that I have above from the work, right? That's the same number. So when we're dealing with a conservative force, we got choices. Well, as long as the conservative force is constant in this case, we can actually calculate the work done only for constant forces, right? Potential energy, we could also calculate. Yep.
I was because it's 10 kilograms, so that makes the 9.8 just 98, and you have 980.
How'd that happen? Oh, I know what the problem is. There's 100, that's supposed to be 100.
Oh, okay.
Yeah, you guys should have called me on that. Like, you need 100 to get 980 newtons for the weight, right? Sorry about that. So, thank you. Very much appreciate that question. So, going back to last class, I encouraged you guys to think about conservative systems. We can do what? We can solve kinematic problems by saying energy before equals energy afterwards, right? But there's another way we can look at that. All right? So, do whatever. I have my eraser. So for conservative force conservative, and to be clear, net force, we need the net force as conservative, right? So if the net force on a system is conservative, then conservation of energy says that the energy initially is equal to the energy finally, right? But what that means is that kinetic energy initially, right, plus potential energy initially is equal to kinetic energy finally plus potential energy in the final situation, right? Now, we can rearrange this equation to relate the changes in potential energy to the changes in kinetic energy. So if I solve for KEF minus KE naught, I get minus PEF minus PE naught. In other words, the change in kinetic energy is equal to minus the change in potential energy. This is another very useful way to characterize conservation of energy. Whatever change there is in kinetic energy for the system must be matched by an equal and opposite change in potential energy. So the net energy flows between these two modes, either kinetic or potential. All right? But in a conservative system, energy is neither created nor destroyed. It only just changes form, is the idea. Any questions? So in this example 3, the change in kinetic energy, minus the change in potential energy is equal to the work done. You're like, wait a minute, why are you talking about work done? You're just talking about changing kinetic energy. Well, I have more good news for you. Theorem. the change in kinetic energy is equal to the work done by the net force. This is a very important theorem. We use this. This is the so-called work energy theorem. This does not have strings attached, in the sense that this is true even for non-conservative forces. I can have non-conservative forces at work. It's still true that the work done by the net force is equal to the change in kinetic energy. I'd explain to you why, but you probably can probably anticipate what I'm about to say, which is that we would need calculus. All right, so that it's derived with calculus. It's not a big deal. I can show you if you want to see it, but I'm not going to do it here. Now, this is you can see this at play, though, right? Because the work done over here, we calculated directly. This is equal to the change in kinetic energy for the situation. And as you can see, that was equal to minus the change in potential energy. There's an example of the conservation of energy as well as the work energy theorem in concert. You know, we can go back to my first example, and with the work energy theorem, we can figure out what? If we know the work done by the force, if that's the net force, right? If that's the net force acting on the box, is that true? Is that the net force acting on the box? What other forces are acting? What is F net for this box, to be careful? Let's think about it for a second. Let's make sure I'm not just selling you a bill of goods here. This is F naught. What are the other forces involved? Gravity. Gravity and the normal force, right? Very good. Those are equal and opposite in this situation. Well, they're not equal and opposite, but they're not equal and opposite. Why? Because, hey, there's a vertical component to the pulling force, right? Which makes the effective weight of the box smaller. It makes the normal force smaller as well, right? I mean, because, you know, if you pull up on a box, you, in some sense, decrease the effective weight in some sense. So the normal force is actually smaller than mg. But you know what happens here? What's the story? I should make it smaller than mg. I don't know. So what we have is that the normal force plus the y component of F is equal to mg, right? Those balance out because the box is not accelerating off the plane, right? But even if they, all right, so great, that doesn't really have much to do with what we're doing. So my question to you is, the net force, what is the net force though? It's equal to F naught plus the force of gravity plus the normal force. Those are the three forces that are acting on this box, because I'm assuming there's no friction. All right? If there was friction, it would change. There'd be another force, right? But supposing we're in the frictionless case for a moment, why, when I think about the net force and the work done by the net force, why is the work done by the net force the same as the work done by F naught? I mean, there's a couple different ways you could look at that. One way you could look at it is all of the parts of the force which are vertical, they're canceling out, right? So the net force is horizontal on the box, right? Another way you could look at it is that the work done by the normal force and the work done by the gravity force are zero. Why? Because those are perpendicular to the motion, right? Normal force and gravity are perpendicular to the motion. So they do no work in this case. So the work is just done by F naught. And we already calculated that work, right? What does work energy theorem tell me? It tells me that the change in kinetic energy is the work done by the net force. So we could figure out that this is equal to the change in kinetic energy, right? And so if I gave you more information about this system, if I told you the mass of the box and I told you its initial speed, you could figure out the final speed, right? Should I do that? Would that make this make more sense? I don't know. Suppose that the box has mass equal to, let's say, 500 kilograms. All right? And V naught, let's let the box initially be what? You want to let the box initially be at rest, or do you want to give it an initial speed? It's up to you guys. What's that? Initial speed, good. So let's let it have an initial speed of, I don't know, 2 meters per second. Well, what we know is that 250 joules, or Newton meters if you like, is equal to the change in kinetic energy. What is the change in kinetic energy? That's 1/2 mass times Vf squared minus 1/2 the mass times V naught squared. I know V naught, I know m. The only thing I don't know here is the thing I'm after, which is what's the speed at the end of this process, right? I want to know what's the final velocity. Can we find that? I think we can. So I multiply by, well, so I have 250 joules. 250 joules plus 1/2, and my mass is 500 kilograms. My initial speed was 2 meters per second squared. That's going to equal 1/2 times 500 kilograms times the speed squared that I don't know. So what's that work out to? 1250, I think. Oh, wait a minute, no. Yeah. 4 times 500 is 2,000. 2,000 divided by 2 is 1,000. So yeah, 1250 joules divided by 250 kilograms is equal to Vf squared. So as a added thought experiment about my example 1, we can learn that if we had that 100 Newton force acting on the box from 0, 0 to 5 meters, comma 0, and if the box initially had a speed of 2 meters per second, then the final speed, given that work done by the box of 250 joules, well, the final velocity would be the square root of whatever this is here. Is that 5? Yeah, 5 meters squared per second squared, so square root of 5. Square root of 5. Phones are neat. So that's 2.236. There you go. So the work energy theorem, but the work energy theorem is much more, has a much wider applicability than the conservation of energy we talked about last class, because work energy theorem is even true for non-conservative forces, right? And one of the non-conservative forces we like to think a lot about is friction, all right? So we have now pretty much everything we need to start analyzing problems that have friction involved, all right? Let's try to look at an example that involves friction and energy and see how we analyze that kind of problem. All right. So let me set the stage here. So here's a problem. So this one's a little bit interesting. Not too interesting though. So, and I'll keep it relatively simple. Suppose that Mr. Top Hat, right, pushes this box horizontally. All right, it's pushing the box horizontally at such a way, all right, that the box moves at constant speed. Is that what I want? Yeah, we can start with that. Let's suppose Mr. Top Hat's moving the box at constant speed. And let's suppose that he follows a path that's laid out by, I need another fictional character. Drake. Drake lays down a line, and the line looks like this. All right? And so Mr. Top Hat pushes the box at constant speed along this line, and let's suppose that that red line I just drew is a kite string, or, you know, let's say it's duct tape. He's laid down this duct tape, and the duct tape, the roll of the duct tape happens to have a length of 50 meters. All right, so 50-meter length. All right, but Mr. Top Hat's always pushing. He's always pushing the box along this path, right, at constant speed. So, you know, over here it's, I can't draw. All right, so, right. And so, you know, and so forth. And so finally he gets over here at the end, and the question I have, at least my starting question is, so 50-meter length, and we're assuming that pushed at constant speed, pushed at constant speed. So then my question is, what is the work done by friction on the box? All right? And also, what's the force with which Mr. Top Hat's pushing the box? So let's analyze this here. So here's a picture of the box at any point. So we've got Mr. Top Hat's pushing force, F naught, like that, right? And we've got the normal force, like so. We've got the force of gravity, which I guess I need to tell you I actually do need to tell you the mass of the box here, don't I? Mass of the box is what? What do you guys want? I mean, this is your chance. I mean, 23. Interesting choice. 23 kilograms. All right. So a mass of 23 kilograms, a very, very interesting mass. Was there a movie about this? Remember. And so you got mg, all right, like so. What's the other force involved? Friction, right? So if you know, if the force is, if Mr. Top Hat's pushing it that way, then the friction force is opposite, right? The friction force is always opposite the motion, isn't it? So this one is where I can actually abuse my initial terms and conditions on what we can calculate, because we don't really need integration here to understand it. We can look at it and go, aha, well, the friction force is always pointing directly opposite the motion, right? So all I have to do is find the magnitude of the friction force and multiply by the distance. That will give me the work done. Is the work going to be positive or negative, though? See, the work's going to be negative because the friction force is always opposite the motion, right? Okay, so what is the friction force? Oh, I guess I need to tell you that too, huh? What we need a mu sub k. What do you want the coefficient of friction to be? 0.5. That's a pretty good choice. It's a pretty good choice. You'll see why I say that in a few minutes. Force of friction, 0.5. So anyway, we have 0.5 times what's the normal force? It's equal to mg in this case, right? So we've got 0.5 times 23 kilograms times 9.8 meters per second squared. That gives me the force of friction, which is what? What? 112.7 newtons. So what's the work done by friction? $112.7 newtons. There's a minus here, right? Times what? What's the distance? Oh, I told you that the path that we're pushing it along is 50 meters, right? That's how long the tape that Drake laid down was. This is worth 50-meter track. All right, let's see here. And what's 50 times 112.7? 5,635 with a negative Newton meters, which is a joule. So there you go. That is the work done by friction minus 5,635 joules. How much work is done? How much work is done by Mr. Top Hat in this process? What's the net work done? The net work done is 0 because it began and ended at the same constant speed. Another really interesting thing about work is additive. So if I have multiple forces producing work, then the net work is the sum of the works done by each of the forces that are at play. Here, there's the work done by Mr. Top Hat, and there's the work done by friction. Mr. Top Hat does a positive work of 5,635 joules. The friction does a negative work of 5,635 joules, right? How about the normal force and gravity? Those also do work in a silly way, right? The normal force does 0 work because it's always perpendicular. What's the work done by gravity in this motion? It's also 0 because we're beginning and ending at the same level playing field, right? There's no change in H. There's no change in potential energy for the gravitational force, which is, that helps us understand why there's no work done by gravity in this motion. All right. Incidentally, power is equal to energy over time, or if you like, you can think about it as work per unit time. Really nice formula. The power is equal to the force dot the velocity. This is the power developed by F on mass with velocity v. So what's the power developed by a force which is perpendicular to the velocity? What does it mean for vectors to be perpendicular, by the way? We say A is perpendicular to B. That is interchangeable with the idea that A dot B is equal to 0, because this means that theta between them is 90 degrees. So if we had a particle under motion such that the velocity was perpendicular to the force applied, the power developed by such a force is 0. No part of the force is in the direction of the motion, and it doesn't develop any energy per unit time for the particle. In contrast, we could calculate, so here's an example. You know, if I had a force of, let's say, 30 newtons minus 20 newtons, and if I have my velocity is, I don't know, 6 meters per second, comma 3 meters per second, I can calculate the power developed by this force on a particle with that velocity. The power is just the force dot the velocity, which would be 30 newtons minus 20 newtons dot product with 6 meters per second, 3 meters per second, which would be 180 joules minus 60 joules. So the power, oh, joules, no. What is the power? Unit of power is a joule per second, isn't it? Energy per time, joule per second. So we got 120 joules per second. What's another name for joules per second? Perhaps I should say, what's another name for joules per second? I'm sorry, I can't take that back. It already happened. Yes, a watt. What is a watt? A watt is a joule per second. There you go. So 120 watts. So we used to have these things called light bulbs. You know, that's about the energy per time an incandescent light bulb you used to have around the house. Yeah, a little bit more, but ballparkish. Okay, so I hope I've exposed, I mean, I wouldn't expect that you guys would be comfortable with these ideas yet. How do you get comfortable with the ideas I'm talking about right now? You got to go and do the problems in chapter, what are we? Chapter 6, right? We need to work on those problems together and come to understanding of these things. So hopefully next class we'll have some time for you guys to ask me questions about the problems in chapter 6, all right? One more example here if I've got time. I may not. Oh, I do. So this problem kind of combines some of the kind of things we were doing last class with the new idea about friction and work. And so here's the problem. You've got an inclined plane, say 30 degrees. You've got a mass up here, all right? And suppose the mass 30 kilograms. It's got an initial speed of 100 meters per second. All right. Let's suppose that this distance here is 50 meters, as pictured, right? So the horizontal distance there is 50 meters, and then the box slides down the plane, and then comes over to here. There's a rough spot. All right. And the coefficient of friction over here is 0.5 again, all right? And the question is, if the box just comes to rest right here, all right, then how long is this rough spot? There we go. That's to remind me, you guys have a quiz. How long is this rough patch? Gotta keep you guys guessing. Now, we're going to assume that this is frictionless. How do you solve this problem? So here's how you solve it. It's a mixture of energy conservation and energy lost. So the idea is this. There's two things. First of all, you got to see past my subterfuge. I gave you 50 meters here. First of all, you got to figure out what's the height over here. That's trigonometry. What's the height of the triangle? If the bottom leg is 50, it's a 30-degree triangle. What's the other leg equal to? Tangent of 30 degrees is equal to the thing we don't know, which we'll call h, divided by 50, right? So h is equal to 50 meters times the tangent of 30 degrees. Point number one. So we can figure out the potential energy from the distance which was given. All right? Then what we're going to do is we're going to say the initial potential energy plus, 1/2 m v naught squared plus the initial kinetic energy. That's the total energy of the system, right? So the box slides down the inclined plane and then across the frictionless plane until it gets to the rough spot, right? That's a conservative process. No energy is lost in the sliding process, right? And then what happens is friction does work on the system in the rough patch, and then all the energy is lost, right? So if you think about that, that means that this energy must be equal to the work done by friction, right? Let's say work done by friction. But that's not quite accurate. I really have to put some absolute value bars there because the work done by friction is negative, right? In other words, the energy lost to friction is equal to the energy we had at the start. But so we've got 50 meters, tangent of 30 degrees, mgh, 30 kilograms times 9.8. So this is mgh, okay? Plus 1/2 times 30 kilograms times 100 meters per second squared equals to what? Now, what's the friction force when it's moving across the rough patch? Force of friction in this situation is just 0.5 times mg because the normal force is mg in this case, right? So we're just looking for 0.5 times 30 kilograms times 9.8. So this is the friction force, right? And the question is, what's d, right? What's the distance it takes to stop it? Let's call that d. So all you got to do is you solve that for d, and that's it. If you look at it, I actually did not need to tell you what. I could have stated this problem without telling you what. Mass, right? That's right. I didn't need to tell you mass. Your book probably tells you mass for such problems because the book is friendly. Yeah? Sometimes I'm friendly. So, I believe that's it for today's lecture. I now have quiz 3 for you guys. You are allowed to have your notes. You can have your notes out since I did not. It's fine. Uh-huh. Just do your best. I will try to give enough quizzes so that at the end of it, if you had like 80% on all the quizzes, you get 100% in the quiz grade. That's something like my target. Did you stop it? Or?
Not yet.
I'll stop it.